So today we have Peter talking to us about energy conservation and holography in de Sitter space.
Yeah, nice. Yeah, thanks, Jesse, for introducing us. Yeah, it's a great pleasure. Yeah, my name is Zhongzhe. You can call me Peter. It's a great pleasure to me to be here in UPAC seminar, and like to thank Bart for inviting me here. Yeah, the topic I'm introducing, energy conservation holography, in De Sitter, is based on a previously published paper on PRL with David Stefanisian, and also based on upcoming work. So first, I'd like to introduce this thing called de Sitter space, and I don't think I need too much motivation. It's probably one of the yeah. Also, please interrupt me at any time and ask any questions. I'm happy to answer. Um, yeah, de Sitter space-time. This is probably one of the greatest experimental discovery in modern science that our universe is not only expanding but also accelerating. And this acceleration is well approximated by this de Sitter spacetime, where we have the Einstein's equation with a positive cosmological constant, and the maximally symmetric solution to that is de Sitter spacetime. And also in the early universe, we believe that there is an epoch of an exponential expansion of our universe, which we dub as inflation, which might also be described by this de Sitter spacetime. So yeah, either in the late universe or in the early universe, de Sitter spacetime has very interesting applications to our real world. So that's why we study it. And yeah, it's very essential to understand how quantum fields or quantum gravity behaves in this particular background, at least asymptotically. And okay, so on the top right corner, this is the Penrose diagram of de Sitter spacetime. It's represented by this square box. And usually in the inflationary scenario, we consider the Poincare patch coordinates, where eta is the conformal time, and usually eta in the inflationary scenario runs from minus infinity to zero. Where at eta equals to minus infinity, we have the usual Hartle-Hawking vacuum, and eta equals to zero is where inflation ends. And h is the Hubble constant, which sets the scale of inflation. For inflation, h is around 10 to the 13 GeV-ish. So it's a very high energy scale. But yeah, for universe, late universe, like right now, current universe, this h is pretty small. Okay, now I'd like to talk about now let's talk about theories, like quantum theories that can live on this background. There's something very distinctive about the Sitter spacetime. That is, there's a discrete set of unitary spectrum, the unitary mass spectrum, that is parameterized by this equation, m squared equals minus delta times delta minus d, where d is the spatial dimension of the Sitter spacetime, times Hubble square, and where delta are positive or non-negative integers. And this is very distinctive because it only exists in de Sitter spacetime. For example, in ADS, such things do not exist. Like there's for ADS, the mass spectrum is continuous, but here there are a set of discrete spectrums. And yeah, for people who are familiar with ADS-CFT, you can immediately recognize that this looks like the form of the ADS-CFT dictionary, where M is the bulk mass and delta is the conformal dimension on the boundary. And one, okay, so look, so these things for positive deltas, for most positive deltas, they're tachyonic, yet they're unitary. So if you quantize it, you actually quantize it at the level of free theory, at the level of 2 point. You compute the norm of the wave function product. You'll find that this is positive. So there's no ghost or non-unitarity going on, specifically for these positive delta integers. And a way to see this is the mode functions do not have branch cuts for these discrete or sometimes called exceptional series scalars. So the mode function is basically the equation, the solution to the equation of motion. And here we're in the momentum time domain, where k is the momentum, the three momentum if we're in the 3+1 spacetime, and eta is still the conformal time. And you can see this mode function is quite complicated. It has some, this is the Hankel function or the modified Bessel function. So in general, this thing has a branch cut and weird analytic structure. But for some specific values, specifically where delta are integers, when delta equals to 3, let's choose the spatial dimension being 3 as well, then by the dictionary m squared equals to 0, the mode function drastically reduced to this simple form. It's a polynomial. Okay, so this is so a rough introduction of scalar theories in de Sitter spacetime is parameterized by this mode function, where we have two indices, delta and d. Okay, good. Now let's talk about natural observables. In the natural observable, there are many names to this. Path integral, wave function of the universe by Hartle and Hawking, or boundary correlators. So essentially, we consider the following path integral, where we have some bulk fields, and we do this path integral. And this path integral is fixed by the boundary condition, where at the asymptotic past, we have the usual Hartle-Hawking state, where at the asymptotic future, the fields decohere, they become classical. And this classical configuration is given by this J here. So J is the classical source. So in the end, the partition function is a functional of this classical source. And here is a diagrammatic representation of what's going on. At eta equals minus infinity, I have Hartle-Hawking state, and these things evolve according to some complicated Schrodinger type evolution, and eventually ends up at eta equals to 0. And at eta equals to 0, fields decohere into this classical configuration. Okay, so this is the usual thing that we consider in de Sitter spacetime, also in ADS as well. There's no problem per se for this path integral or wave function of the universe, but one problem is that this thing is sensitive to boundary conditions. More importantly, this thing is not gauge invariant. If you do a diffeomorphic transformation in the bulk, this thing will alter the things on the boundary at eta equals to 0. So this partition function, this path integral, is not gauge invariant. It's also not field definition invariant. If you change your field basis by a small amount, it will completely alter the boundary condition. So if we're someone who purely cares about how bulk evolution works, we should not consider this path integral because it's too sensitive to too many redundancy transformations. So this is what motivates us to study the following object. Is originally proposed by Yaniv and Enrico. This is called de Sitter S matrix. In the usual Poincare patch, the conformal time runs from minus infinity to 0, but now we're extending this to plus infinity. So now this coordinate, this flat slicing patch, is going to cover the entire de Sitter spacetime. And so now at eta equals to minus infinity, we have this Hartle-Hawking state, or we call the Bunch-Davies vacuum. This vacuum highly resembles flat space scenarios, highly resemble flat space vacuum. Actually, this is precisely how they are constructed. So now we can prepare some in-state and out-state at eta conformal time equals minus infinity or plus infinity. Both at eta minus infinity or plus infinity, we have some asymptotically well-separated states. We can have our usual cluster decomposition ansatz for scatter amplitude. So now what we do is that we prepare some state at eta equals to minus infinity, and the states evolve. And another thing I want to mention is that this metric, despite being singular at eta equals to 0, actually the singularity is just a coordinate singularity. There's nothing real here. If you compute any some scalar quantities using this metric, for example, Ricci square, R mu nu square, or R mu nu rho sigma square, none of it will diverge. Actually, all of them are going to be just a constant proportional to the radius of de Sitter. Okay, so the scatter amplitude is defined by preparing in-state at eta equals to minus infinity, and this thing evolving across to the conformal boundary, and now it crosses it. After crossing the conformal boundary, it ends up at the contraction patch. So the lower triangle is called the contraction patch, and the upper one is the expansion patch. And after entering the expansion patch, the contraction patch, it ends up at eta equals to plus infinity. So at both eta equals to minus infinity and plus infinity, we have asymptotic states. So we can define the S matrix to be the usual LSZ reduction of the correlator. So this equation just defines the S matrix, and the S matrix by default is Fielder definition invariant. We've shown various highly non-trivial examples in the paper, but I'll not belabor here because I don't think I have the time to do it. So this is the S matrix. It's completely analogous to what we have in flat spacetime, where we have some in-state and out-state, and both these states sandwich the time-ordered Schrodinger evolution operator, this unitary evolution operator. The major difference is that now the interaction Hamiltonian contains explicit dependence on the conformal time. So there's no time translation in de Sitter spacetime. So in general, by Noether's theorem, we shouldn't expect that the scatter amplitude will conserve energy because of the explicit time dependence. In flat space, in the collider physics or any flat space scatter amplitude, this H interaction is completely it doesn't have explicit dependence on time. Okay, so this is just the computation that we are going to carry out. Okay, another thing I want to mention is that this construction is completely adoptable in ADS as well. In ADS, we have a similar thing to do. We just usually in ADS we consider the Poincare coordinates where z runs from 0 to plus infinity. But now, in order to cover the entire ADS global patch, we need to extend z to minus infinity. And these two conformal boundaries are identified. So in ADS, analogous construction can be carried out as well. So yeah, there's nothing too special about de Sitter space in that sense. Okay, now we have the scattering amplitude prepared. Now let's do some real physics. Consider a spectrum in the discrete series. So let's pick delta equals to 4 in 3+1 dimension. And according to the dictionary, the m squared equals minus 4h squared. This is the next to massless value. Like this is the next one to massless. For massless, is delta equals to 3. Now we move delta by 1, and mass square equals minus 4h squared. H is the Hubble. So this is the mode function. We solve for the free equation of motion. We get this this thing. You can see that although it's slightly more complicated than the massless case, it's still pretty controllable because it's still polynomial in this case and etas. So the interaction now, I'm just writing down some random effective field theory action. The first two terms are just the connected term plus the mass term. It's completely fixed up to, by our normalization convention. And now I'm adding some 4-point interactions. So I'm just writing down random things up to 4 derivatives. I have some phi-4 interaction. I have some phi squared d phi squared interaction. I also have some d phi to the 4th interaction. And each of them are associated with one Wilson coefficient. And right now, these coefficients are completely unfixed. And the last term can actually be removed by a Fielder definition. In the paper, we actually calculated the scatter amplitude contribution from this term. It turns out that it's completely degenerate with the other two. So at 4 point up to 4 derivatives, there are only 2 independent operators up to Fielder definition. Okay, so now let's compute the Dyson series. So this is the previous this X matrix computation. We just Taylor expand this, like what we do in flat space. We expand this time ordering. We expand this interaction Hamiltonian. So after doing that, these are the type of integrals that we're trying to compute. And in flat space, you can see there's an explicit polynomial dependence on conformal time here. In flat space, we don't have such thing. We just have the phase factor. And this KT here is the sum of all the energies. And in flat space, if we ignore this polynomial dependence on conformal time, we just perform this integral, we just get the delta of KT, which is the energy conservation condition, where in flat space is always satisfied. But now, because we're in de Sitter, there are some explicit time dependence. So in this particular case, this number p here, the degrees of this polynomial runs from -8 to 4. So what's the most interesting bit are, of course, when eta is singular at eta equals to 0, because there's a divergence, and we need to tame them. Uh, so we need to perform some regularization procedure to regularize this integral. What we do is, okay, first, we care about the real axis integral. So we want to integrate, oh, this is the complex conformal time plane. What we want is we want to integrate over the real axis. And because there's a pole at that the only non-analyticity lies in the pole at the origin where eta equals to 0. So what we do is that we either go from above the pole or we go from below the pole. So this is just a regularization scheme. Different regularization scheme yields different boundary condition, correspond to different boundary condition. And after this small contour deformation, we can enclose the contour such that the large arc vanishes. So the real axis integral that we care about equals the large arc integral, which is 0, plus the residue. If we enclose for example, on the left graph, if we enclose the contour from below, depending on the sign of kt, the whole contour encloses a pole which yields a residue. But if kt is smaller than 0, we enclose the pole from above. We enclose the contour from above where there's nothing enclosing. So it actually yields 0. So these two graphs just gives us a theta function, a step function, where theta is 0 for when the argument is smaller than 0, and theta is 1 when the argument is bigger than 0.
Wait, sorry,
Okay,
could you say
sure.
again, why do you choose the particular upper and lower
Good. Yeah, there's
arcs?
no
Yeah.
principle. Like, yeah, each of them correspond to different physics. Like, yeah, this is imposed by the boundary condition. Well, this is the boundary condition we choose. Yeah, this is a good question because in the end, we're going to see that the counter dependence cancels by some stipulation of ours. But in general, like for generic theory, in order to regulate this integral, you need to choose a regularization scheme. And this is the whether it's upper or lower is the scheme dependence, our regularization.
The purple arc is scheme dependent, but the orange and green arcs, those are depend on the boundary conditions.
No, these do not. Okay, good. So
Yeah.
the principles of choosing the big arcs is such that this integral vanishes. This integrand vanishes at infinity. So it actually only depends on the sign of kT, which is the total energy. For example,
Oh,
is if
true, I see. Yeah.
yeah, good, good. Yeah, this is scheme independent. It depends on what kind of kinematic configuration we have. Yeah, it's chosen such that this thing just vanished. It's a computational technique. We actually do not
Okay, I
need to
see. Thank
enclose the
you.
counter. We just need to compute the real integral. And this is, yeah, okay. Any other question? No, okay, good. Okay, so the scatter amplitude takes this schematic form where we have some non-energy conserving amplitude coming from this surrounding the poles, and we have some energy conserving terms coming from this polynomial, this positive powers of polynomials in conformal time. So in flat space, what we have is just a singular delta of kT. Because in de Sitter, we have some polynomial, like positive powers of polynomials dependence on eta. When Fourier transform, these positive powers of eta becomes derivatives. And so we have a collections of derivatives of eta as well. And each of them will correspond to a scattering amplitude coefficient. Yeah, this is suggesting that physics in de Sitter is way more intriguing than what we have in flat space. Yeah, simply because there are more structures. Okay, so however, this non-energy conserving term is more interesting because this is something that we would never encounter in flat space-time. So this is the form that it takes. The second line here is just some ugly kinematic dependence. We don't care about them too much. The first line is more interesting. First, notice this is plus or minus sign. This theta plus or minus kt correspond to the previous counter deformation that we alluded upon. That is whether we go from above or below. So yeah, so this plus or minus sign, this ambiguity here is the scheme dependence. A more interesting bit, well, it's not more interesting, but another interesting feature is that you can see that this d0 is the Wilson coefficient associated to the potential phi fourth, where this d4 is associated to the Wilson coefficient d phi to the fourth. And these two terms in flat space, these two terms never talk to each other. They have different power scaling. So, but in De Sitter, because of scale invariance, because De Sitter contains scale invariance and the special conformal transformation, special conformal symmetry, these two operators are actually linked together. So yeah, that's another reason why De Sitter or ADS physics is more interesting than flat space, is because there's more rooms for interplay among different operators. Like operators with different power scaling can actually talk to each other. In this case, we can see that they precisely yield the same kinematic dependence. Okay, good. Good. So now let's talk about this theta term. This seems really odd, really bizarre, because it is. Because what does this theta term means physically? It means, for example, if we choose the plus sign, it means energy can only be created. So you can only observe positive energy in your eta equals to plus infinity asymptotic future.
Hi,
And
Peter, can I ask you a question?
sure.
Can you go back to the previous slide?
Yes.
Yeah, this one. Is there, can I have a case where this yellow prefactor cancels out to 0?
Precisely. Yeah, this is what I'm going to show here. Yes.
So is there a symmetry? Or what's the symmetry?
Precisely. Yeah. Okay. Yeah. It's exactly what I'm showing.
Okay.
This slide.
Okay. So
Good.
I'll wait. I'm
Yeah.
sorry.
Nice.
Thank you.
No problem. Yeah. Good. So this is so what all I'm leading to is to say that these factors need to cancel. Yeah. This is exactly what I'm trying to say. So this term corresponds to eternal energy creation or annihilation. This doesn't sound stable. A more precise statement is that when we compute the scatter amplitude and now we integrate against over a phase space to obtain a cross section, because in flat space we have this energy conservation to protect us from going too far away. So the whole momenta are localized on the sphere by energy conservation. But because of this presence of this theta term, it actually just diverge. So when you compute the cross section, it doesn't make any sense. Like it's completely divergent. So it kind of violates unitarity. So we want to eliminate this term. So by eliminating this term, for all kinematic configuration, we need to tune this coefficient, like d0 equals to minus 8 d4. And this seems to be an arbitrary choice. But however, and also another thing is that, this is related to what Jesse was asking before. The counter dependence canceled in this case. If we choose d0 equals minus 8 d4, then this theta term cancels. And this theta term represents the counter dependence. And since there's no theta term, there's no counter dependence anymore. So now I have a unique answer. And again, this coefficient tuning, what does it correspond to? It turns out that it precisely corresponds to the Dirac-Born infill theory in De Sitter spacetime, up to a Fielder definition. So what is Dirac-Born infill theory in De Sitter spacetime? It has a geometric interpretation. That is, if I have a De Sitter forebrane embedded in an ADS5 bulk, and the fluctuation on the De Sitter forebrane along the extra dimension is parametrized by a scalar. And the action of the scalar is precisely this form. And you Taylor expand this form, at 4 point, you find this action up to a Fielder definition. So what we did is that without knowing anything about geometry, we're able to uniquely pin down the 4-point interaction of the Dirac-Born infill with up to a Fielder definition. And leading to what Bart was asking, what is the symmetry of this DBI? Yeah, this theory can either be formulated in terms of a geometric language or an algebraic language. So this is the symmetry. The symmetry, yeah, as I said before, like the ambient spacetime in terms of geometry is ADS5. So it's the isometry is SO41. But in the end, we only have a linear de Sitter symmetry realized on the brane. So it's a symmetry breaking pattern from SO42 to SO41, and the broken generator is parameterized by a vector here. And this vector is realized, this vector symmetry is realized on the scalar by this. So this is actually the fifth dimension Poincare boost realized on the scalar. Okay, does it answer your question, Bart?
Yeah, thanks.
Okay, good. So yeah, okay. Also, I need to explain what these boxes are. So this is the de Sitter isometry. So in the Young diagrams, the vertical columns correspond to antisymmetry. So it's kind of the de Sitter isometry. It has an antisymmetric tensor. Let's call it LAB, where AB are antisymmetric, and this is just a vector, which is parameterized by this SA here. And notice that this is a violation of Goldstone theorem, because Goldstone theorem is saying that the nonlinear, the broken generators, the number of broken generators are equals to the number of Goldstone fields, but that's for internal symmetry breaking. For spacetime symmetry breaking, because this generator has some non-trivial interplay with the de Sitter isometry, so some of the Goldstone modes are actually just dependent, are degenerate. In the end, we only have one scalar here. Okay. Good. So now let's try the next mass value for the exceptional series where delta equals to 5 and m squared equals to minus 10h squared. Now I'm adding another term. Well, I will not I'll not be overarching on how many why am I adding this term, but it's just another higher derivative term. And by some argument from flat space, we know that there's only one independent term up to Fielder definition at 6 derivative. So recall that previously we add to up to 4 derivative. Now I'm adding another 6 derivative term. So if we do the same game and also this tuning, what we are dubbing as is generalized energy conservation, GEC yields this particular coupling tuning. So now I have 3 free Wilson coefficients, and 2 of them are uniquely fixed, leaving us with a unique scale, which is let's call it D0, because D4 and D6 are uniquely determined by D0. So we rediscovered the de Sitter special Galilean. So the de Sitter special Galilean, I don't think it has a geometric formulation, but it does have an algebraic formulation. The algebraic formulation is this. So before, for the DBI case, we have a single box, which is a vector. But now this symmetry is enlarged into this. Now it's a traceless symmetric tensor, SAB here. So this is the full algebra. The full algebra is actually a special unitary group. Is SU5, I believe. Yes. So it's the symmetry breaking from SU5 to SO41. Or from a Lie algebra perspective, is SU5 goes to SO5, or in Euclidean signature. Okay, so yeah, the punchline is that without knowing any of the symmetries, just by demanding this simple equation, we're able to uniquely pin down all of the interactions. Well, up to 4 point. I believe that if we go to higher point, we can fix them as well, but it's too hard of a work to do. So yeah, I'll probably skip this slide, but this is something that you should not take too seriously. But what I'm trying to argue is that by demanding the spectrum, in this case, is a scalar or some with a particular mass, and the stability requirement, we are able to uniquely find DBI and special Galilean. On the other hand, it is well known that Yang-Mills and general relativity are uniquely defined by the stability requirement, like namely no ghost. Yeah, by demanding, for example, for a massless spin 2 theory that doesn't have a ghost, we can have the linearized Einstein-Hilbert, and then up to higher order, we can just build the whole Einstein-Hilbert action by demanding that ghost vanishes at each order. Okay, so yeah, I'll just go through motions for here. If I just increase delta equals increase the deltas, the conformal dimensions, which correspond to a higher mass spectrum, and add more derivatives to the operators, we're going to find that there's another unique solution. So now we have 4 free coefficients and 3 of them are fixed. So this is qualitatively the same as the previous 2 theories, where it's parameterized by a single coupling, and there's no deformation. Yeah, the only deformation can come from are the irrelevant operators. All the relevant operators are completely fixed with these beautiful coefficients. Okay, so yeah, we can just play the game once again, adding derivative up to 10 derivatives, adding up to,
Silly question, Peter.
sure.
Is there some pattern in these numbers? Just a
No,
question.
yeah, actually, yeah, these numbers are actually dependent because it depends on how you choose the operators. For example, at 6 point, I can choose another at 6 derivative, I can choose another operator where
Okay.
these derivatives are distributed differently.
Okay.
So these numbers are not unique. So it's only up to a basis. So the only unique thing is actually the amplitude. So yeah, so probably some coefficients of the amplitudes are unique, or maybe one can find some pattern. But these numbers, I don't think they have patterns. Okay,
Okay, I see. Thank you.
good. Okay, yeah, if we just keep playing this game, and we just found another unique answer. Like now it's more remarkable because we have more and more coefficients, and all of them are fixed. And it also kind of it corroborates with the EFT paradigm where the higher derivative terms are suppressed. Look at this number. This number is very small. So, and this is the coefficient associated to the 10 derivative terms. So, yeah. So, yeah, it's a nice check, maybe. Okay, so what are these things? I just writing down random things, right? These things right now they don't have any meaning. It's a solution to this equation. But is there any deeper meaning to these theories? Like are there even complete theories? Because right now I'm only doing 4 point. What if I go to 6 point, 8 point? Does this paradigm break down? The question is we don't know. But there are hints towards these theories. It's actually by these 2 papers. So basically, the idea is that there's a humongous higher spin algebra, and this algebra can be break down into the usual de Sitter isometry and all the other complicated stuff. And these complicated generators can be realized on some fields. For example, these things with a single rule correspond to scalars. Things with one other rule, with 2 rules, correspond to higher spins. And for example, this guy is it's a mixed tensor. It corresponds to a vector. It's a massive vector. And this guy, this box here, correspond to a tensor. It's a massive tensor, so it's a massive graviton, something like that. So yeah, but this theory, despite knowing the algebra, the realization on the field is completely unknown. So yeah, this has only been briefly discussed in these 2 papers that the algebra exists, but we don't know whether there's a theory. But so what I'm showing here is actually just the first step towards discovering these concrete theories. Okay, so this is just a midpoint summary. Okay, it's 36 minutes. Good. So yeah, we have delta equals 4, delta equals to 5, and delta equals to 6 upon literature search. I did not find any. And delta equals to 7, we have this big thing. And this tower is very unlikely to truncate. Okay, any question up to this point? No? Okay, good.
I have a quick question.
Sure.
It reminds me a lot of Young Tableau. Is there a connection between that and this?
Between what? Between Young Tableau and
Young Tableau and this sort of representation diagram?
Yes, good. Yeah, good. Okay, good. So this thing with 2 boxes lying vertically is the adjoint representation, and this is the fundamental, or yeah, can you see my cursor? Yeah, right. Yeah, this is the fundamental representation. Yeah, actually,
I see. Yeah.
And this is the traceless symmetric representation, and this is the rank 4 traceless symmetric representation. And yeah, yeah, basically these things parameterize the representation. Yeah. And
Okay,
and
yeah,
this
that
is
makes
the
sense.
and these things are the representation of SON, let's say in this case, because our isometry group is the adjoint represent. Yeah, because the building block is de Sitter. De Sitter is SO41 or Euclidean de Sitter, let's say SOD here, and SOD has the adjoint representation. Well, the de Sitter is parameterized by the adjoint representation of SOD. So yeah, everything here is SOD. Yeah, the irreducible representation of SOD. Good. Okay, now let's move on to holography. Yeah, so basically what I do is I briefly introduce what holography is and how it's and I'm going to reveal an connection between holography and the scatter amplitude I mentioned before. So yeah, so this is the holographic duality, where on the left-hand side, I have a QFT partition, a generating function, and on the right-hand side, I have a gravity partition function. So the gravity partition function is precisely the same as what we mentioned before. It's some evolutions from the Hartle-Huggins state to some fixed boundary field value. And this thing computes the path integral between these two boundary conditions. And on the QFT side, we have some quantum operators coupled to this source phi bar. So basically, these 5 bars just mobilize the entire QFT. And it's important that these 5 bars are classical. So in the string theory picture, it's kind of like I have some bulk fields that they decohere at the ADS boundary, and these decohered classical fields source the quantum operators on the boundary. A thing I want to say is why am I saying it's QFT, not CFT? Because usually when you couple your quantum operator to a classical source, it induces a conformal anomalies. So this quantity here, either quantity is conformal invariant. If you add the conformal word identity on these things, it will not vanish. You can only obtain an invariant answer by adding an beta function. So yeah, these things are truly QFTs. They are not CFTs. And both sides diverge. So renormalization is absolutely necessary. And another thing is the UV cutoff of the QFT side can be identified with the IR cutoff of the gravity side. And I'll illustrate that point by making an example later in the next slide. So usually we consider the boundary correlators. It's defined by taking the functional derivative of the path integral with respect to the classical source, and eventually sending the classical source to 0. Okay, and here is an example. I'm juxtaposing these two cases, QFT and gravity. So let's consider a complete, just a toy model, where in the CFT side, I have a free theory. This is a 3-dimension free scalar. And let's consider some operator O equals defined by phi to the 6. And the dimension of that is 3, because at 3 dimension, the free scalar has conformal dimension half, and times 6 is 3. And by the dictionary, the m squared equals to 0. And d is the is the spatial dimension. Oh, sorry, it's the boundary dimension. And on the gravity side, I have some free scalar with a phi cube coupling. So these things, we are going to see that they're the partition function computed on both sides are the same. So now let's compute this 3-point correlator. So let's first focus on the left diagram, where the external legs correspond to the classical source. And from each point, we can see it stretches out 6 legs. And those 6 legs correspond to the phi 6 operator. And this is the only diagram we can draw. Actually, so this is a complete non-perturbative. This is non-perturbative. This is a complete answer. It's not a perturbative Feynman expansion. So you can see that this loop integral has, there are many loops here. So usually we encounter a loop integral, we need to cut it off at some high energy. And we parameterize that high energy cutoff as 1 over epsilon. And this is the QFT side. And on the gravity side, I have some Feynman-Witten type of diagram. So these things just emanates from this lambda phi cube term. And we compute the path integral and integrate up to the boundary. But when we integrate to the boundary, there's going to be divergence. So we need to cut the boundary. So it's another regularization scheme. And the size of the boundary I'm cutting is parameterized by this epsilon. And we can later see that these two epsilons are identified. So that's what people mean when we say that the UV cutoff of a QFT equals the IR cutoff of a gravity. And this is it. Okay, so we need regularizations. Regularizations is just, there are many regularization schemes. Usually, the most two dominant ones are the finite cutoff reg and the dimension regularization. And after regularization, we also need to renormalize. The renormalization is usually performed by renormalizing the source. So the source can be renormalized by just a redefinition. The redefinition sometimes may depend on the quantum operator as well. So, and there are some constraints on this renormalization. That is, by locality of the boundary field theory, the counter term has to be local in the boundary with no reference to the box. So everything needs to be covariant. Everything this F depends on has to be covariant with respect to the boundary metric. And that's going to be a powerful constraint, as we're going to see later. And this is weakly related to the factorization problem, which also stems from boundary locality. So basically, a factorization problem is saying that if you have two disjoint union, you compute the partition function and it will factorize because this two disjoint union on the boundary do not interact with each other by locality. Okay, so this is the type of renormalization we need to do for the previous, the aforementioned case. Phi bar goes to phi bar plus some renormalization scale dependence and epsilon, the regularization scheme parameter, times phi bar square. So this is a very standard Fielder definition. And the renormalized boundary correlator takes this form. And we can see that there is an explicit dependence on the renormalization scale mu here. And the conformal anomaly is defined by A equals mu d mu acting upon this 3-point operator, yielding this answer. These cases are just the momentum of the operator. Okay. Good. Now I'd like to compare what I have done for the scattering amplitude and the boundary correlator. It turns out that the integrand that we're using to compute the boundary correlator and the scattering amplitude are completely identical because they're just Feynman diagrams. They're just Feynman-Witten diagrams. So we have some bulk-to-bulk propagator, bulk-to-boundary propagator. Everything are exactly the same. And on the top side, we can see that, there's a 1 over z to the d. This is the measure, the square root minus g. And all the interaction details are captured at this capital F here. And for the boundary correlator, where the only difference between the scattering amplitude and the boundary correlator is one, for scattering amplitude, I'm integrating from minus infinity to plus infinity. However, for boundary correlator, we usually consider the Poincare patch where we integrate from 0 to plus infinity. And so on the top side, which is the boundary correlator, we have a log dependence, and the coefficient in front of the log is the conformal anomaly. On the scattering amplitude side, we have this non-energy conserving amplitude times this theta. And there's a very nice distributional formula that's saying the logarithmic of a number plus or minus I epsilon equals the principal branch of that log of that number minus plus I pi theta. So it turns out that these two things can be identified, and it's precisely identified by they're the same. So A equals A here. So A, the conformal anomaly, equals the non-energy conserving amplitude. And this can also be testified by the following just colloquial statement. We have field redefinition invariance of scatter amplitude. So A here does not alter upon doing a field redefinition. And also we also have the non-renormalization theorem for conformal anomaly. And recall that the renormalizations in the boundary perspective is just a field redefinition in the bulk. So these two statements can be related to each other. So this is a nice just a verification of this above statement. And yeah, okay. So now I'm introducing another what was it called? Another consistency relation. So the path integral can be normalized by a local in-boundary field theory term. This is what I have been alluded to. Therefore, it puts constraints on the conformal anomaly A here. So not all A's are allowed. Only a subset of A is allowed because some of the A's might not be renormalized by a local in-boundary field theory term. And recall that the generalized energy conservation corresponds to the vanishing of this non-energy conserving amplitude. And by the identification, A equals A here, we can conclude that GEC is a strict subset of holography. Because, yeah, conformal anomaly can exist in holography, but not all conformal anomaly can exist. On the amplitude side, the conformal anomaly has to vanish. And this is argued, and actually GEC is a measure zero subset of holography. So yeah, this is a summary of that. GEC as a stability requirement of de Sitter vacua suggests that GEC lie in a strict measure zero subset of ADS vacua, because GEC actually does not impose any condition on ADS, because in ADS we have time translation, and energy is always conserved. Yeah, because the boundary field theory is the boundary is time-like. So the ADS metric just have boundary time translation. The same transfers to the bulk, and it doesn't impose anything. So the fundamental building, like the guidance for building an ADS effective field theories should be holography. And holography just translates into some analyticity constraints on the conformal anomaly, where GEC is suggesting that A equals to 0. If we believe in de Sitter CFT, then it corresponds to some conformal fixed point, because conformal anomaly vanishes. So in the boundary, we have an actual conformal field theory that does not flow. Okay, so this is one example of non-holographic consistency. Yeah, let's consider this 3-point correlator where the first operator has delta equals to 4, and the second two operators are delta equals to 2, and they're identical operators. And this is after regularization, we can see there's a log term, and this log term needs to be renormalized. And there are some kinematic dependence, and this K2 square term, let's say the first term, this K2 square, K3 square, K1 square, this can be normalized by a box phi bar. Because K square is just defined by square root gamma ij, Ki, Kj, where gamma ij are the boundary metric. In this place, it's just the Minkowski or Euclidean metric. So it can be renormalized by something like a box. Same for K3 square and K1 square. However, the last term, you can see that it's K2 times K3. So this term needs to be normalized by something like square root box and square root box. And these are non-local. So it turns out that these things, this correlator cannot be renormalized by a local encounter term. Sorry, local in boundary counter term. And the level of 3-point, actually, these things can be completely extrapolated from the external configuration. That is, when the external configuration satisfies this condition, which is called the super extremal condition, where delta I plus delta j plus 2n, where n is a positive non-negative integer, equals delta k. For example, in this case, 2 plus 2 equals 4, and n equals to 0. And yeah, so whenever you see such correlator, it's not holographically renormalizable. So in any holographically consistent theory, these correlators should be 0. So on the gravity side, it means the Wilson coefficients needs to precisely tuned such that this type of interaction do not arise in the first place. Okay, so here is a new 4-point interaction. This is just to provide an example of how GEC is a measure zero subset. So yeah, this is just some random things I've chosen, where I have some 5, 5. 5 just correspond to the conformal dimension. I have some, yeah, the 4-point interaction involves 1, 5, 5, and 3, 5, 2, where 2 is also the conformal dimension. Yeah, it's a conformally coupled scalar, delta equals to 2, and delta equals to 5. I'm adding up to 6 derivatives. And by imposing GEC, we can see that 2 of the coefficients are uniquely fixed by the third one, and leaving us with a unique theory up to a scale. And the scale is parameterized by C6, let's say. And this is very likely to correspond to a new symmetry that we don't know yet. And on the other hand, holography is telling me that C0 equals this thing. And one can easily, and there's only one constraint. So it's a 2-dimension parameter space in the end. And we can easily check that holography is a measure zero subset of GECs. Okay, yeah, this is probably one of the last slides. Yeah, good. So now, yeah, this is a bit of a leap. I'll not in detail, yeah, I'll not introduce this vacuum construction in details, but this is one alleged ADS scale separation vacuum. It stems from this massive type 2A ADS4 vacuum. And the distinctive feature for this thing is that it has some finite massive low-lying moduli. So anything above this thing is hierarchically bigger. Yeah, for example, in ADS5 cross S5, the prototypical example of holography, there's no scale separation because we have from massless scalars up to infinity. There's no hierarchical scale separation. But this case, there might be. So this is why people are interested in this vacuum. And the low-lying moduli for one particular vacuum, the low-lying moduli have this conformal dimension. So the 4-point interaction, I just schematically write it down up to 4 derivatives. By imposing holographic consistency condition, I can uniquely pick out C4. So if this theory constructed by these string theorists are holographically consistent, the 4-point interaction should have the following coefficient tuning, where the 4 derivative terms is fixed by the 0 derivative term. Okay, so yeah, this is one way from the string theory side. It is by checking whether a thing is holographically consistent or not is one way to check that if this theory is actually stable or not. We believe all holographic theories are stable. Yeah. Okay, so this basically concludes. Yeah, these are just some open questions and future directions. Yeah, we have some scattering amplitude, which are field basis independent. It's robust against any field redefinition. So can we have something in holography as well? And correspondingly, in the boundary theory, we should have some renormalization group flow invariant path integrals. And will there be application in collider or condensed matter? I don't know. And there are some concrete theory construction. Yeah, recall that there was a previous humongous algebraic structure, and that theory is hopeless to construct. So we move to lower dimension to construct a simpler theory. So this is the theory that we're currently constructing. It's a de Sitter 2 theory with a single scalar, where the scalar has the following symmetry. And what we are trying to figure out is what this ... is. So it's a symmetry breaking from SO5 to SO3. Okay, so what? Also another question. This is very elusive. What is the full embedding of that in quantum gravity? And yeah, another thing is that is there any what are these holographic dual to condensed matter? Because all of these theories, DBI, special Galilean, all the other things I've discovered correspond to conform a fixed point on the boundary. So there should be some strongly coupled quantum mechanical system that correspond to these bulk theories. And yeah, question is, what are these things? Yeah, these are questions that I'm hoping to answer in the following research. Okay, that's basically it. Thanks, everyone.
Great, thank you. That was very interesting. I guess people can ask questions.
Yes, any question?
Hey, Peter,
Hey.
do you recall if this ADS vacuum that you mentioned for type 2A, if it's supersymmetric or not?
This particular one is not. Yes, there are many supersymmetric ones and non-supersymmetric ones. I'm choosing a non-supersymmetric one. Yeah, this particular one is not.
Okay, can you then elaborate what you mean by holographic consistency implying stability?
Well, I think it's a conjecture. I think usually, yeah, what do we mean by a theory that's non-holographic? It means that the brain does not decouple from the bulk, right? So everything is very entangled. So there's no asymptotic boundary to that thing. So you might construct something that seemingly the brain is located far away, but actually some corrections or quantum corrections we might just drag that brain back. So it's not actually a stable solution. So a diagnosis of whether a thing can be stable or not is to check this type of conditions, whether this thing is holographic or not. But this, yeah, it's not concrete. It's not like there's no like a proof of that, like saying that this thing, if a thing is holographically consistent, it has to be stable. But this is something I believe the community believes in.
I'm a bit confused. So when you're saying that, but you're talking about the stability of a brain here. But if I recall correctly, these types of type 2A vacuum are like DGKT style.
Yeah.
It comes from compactification, not from a brain. So
Yes, true. Yeah. Yes. Yeah, good. Then it's probably, yeah, it's not the brain in this
and
case,
also
I think.
if they're non-supersymmetric, I would assume this is also conjectured within Swampland that non-supersymmetric ADS vacuum are generally not stable.
Okay, good. Yeah, I think if they check the 4-point interaction and if they do not look like this, then it's not stable. Yeah,
It's
this
not
is
stable.
just,
Okay.
yeah.
And then you would say that that's because it's not holographically consistent.
Exactly. Yeah, it's just, yeah, it's a different vantage point. Yeah,
Okay.
yeah.
Cool.
Maybe a related question. Would you be
Sure.
able to clarify what you mean by stability in this context? Yeah, like you say, I'm not quite sure I understand.
Yeah, I think I don't understand that either, but this is just yeah, I don't know how explicitly one would check from the string theory side, but from a low energy effective field theory side, I believe this is something that we need to check, that whether a thing can be holographically or normalized or not. Yeah, I don't think I have a more sophisticated answer to that.
Oh, okay. I was just wondering, say, like you say stable, like what exactly would be the thing that is stable or not stable? Like a particular configuration or?
Well, let's say you construct okay, let's say you take a supergravity action, you compute the equation of motion, and you have a vacuum configuration. And this vacuum might be stable at the lowest order, let's say tree level, but maybe at higher orders, there's infinite back reaction to just destroy this vacuum. And I think what we believe is that if a vacuum is stable, it has to be holographic. So yeah, holography is kind of like the the bedrock of these things. Like we believe any ADS vacuum has to have a holographic dual. So it has to
Oh,
be
I see.
described by some
Okay.
CFT. So if it's not described by a CFT, it's probably not stable. Yeah, this is kind of what I mean.
I see. So it's the vacuum itself is stable,
Yes,
not
yes.
stable, etc. What would it
Yes.
say, like, with your example, what could the vacuum decay into if it say wasn't stable?
No, I have no
Yeah.
idea. I absolutely have no idea.
Yeah, that's
No.
okay. Because it sounds strange, like using ordinary language.
Yes, I think it's also debate. Yeah, I think a lot of people in the swampland community are trying to falsify this vacuum. Like it's saying that in ADS there's no scale separation because of some swampland distance conjecture. So yeah, this is just providing further tools for them to identify whether this thing can be achieved or not. Yeah.
Cool, thanks.
Yeah, what are they decaying to? I have no idea. Yeah. I actually don't think that even string theorists have any idea of how these things work, but I cannot be sure.
Yeah, maybe I can comment. So I think we understand sort of on the gravity side, ADS decay quite well.
Oh, really? Okay.
But I think it's the holographic dual story that's not really known. I think I can't speak on behalf of everyone, but probably my own thought is that it's not going to be a dual to a CFT.
I see. I see.
Yeah.
Maybe you could go back to the slide where you look at the symmetry breaking.
Yes.
So yeah, I
This?
think
Good.
yeah. So for this the special Galilean, you still get one boson?
Yes, exactly,
Okay,
exactly.
yeah.
Yeah, exactly. It's one scalar.
Okay, yeah.
And it's realized by this. So you can see that in the end, there's no index left. Like SAB is contracted with XA and XB. X are just the coordinates in the ambient space. Ambient space is flat. And yeah, so it's realized on a scalar.
Okay. And what was the group breaking here? It was
Yeah, this is a big SU group breaking to SO group. For example, SU5 breaking to SO5, or SL5 breaking to SO5. SU and SL, they're kind of the same at the Lie algebra level.
Okay.
Yeah, and this is some super big SL group, I believe. And there are also some exceptional group breaking down, like some E8 group breaking down to this type of things. But yeah, it's hopeless to construct these theories explicitly. These are actually the only known examples. These two, DBI and Special Galileo. And DBI, we probably know it for like almost 100 years. And yeah, Special Galileo is more novel, it's more recent. It's from this massive gravity thing stuff. Yeah.
Thanks. Very interesting.
Okay.